So now what I am going to do is, I am going to show you the execution flow of this program. Okay. So all my code I will be assuming is in addresses like C100. So this is a hexadecimal number, right? Code segment, right? And this is just the EIP, the offset address, not the segment register address. That is a different thing, right? So I am just assuming that this is a 16-bit number. Each digit is a hexadecimal number that gives 4 bits. So it's a 16-digit number. If you want 32, you can just append it like this. Okay, but to keep it simple, I am just going to call all the addresses as 0xC100 or 0xC200, something. Okay, some random hexadecimal assignment I am doing for the addresses so that we can figure out what's happening. So in C100, okay, I am assuming that instruction move Z is sitting. Okay, so look at where EBP is pointing. Okay, so EBP minus 4, right? So what is this? This is going to be EBP minus 4. Okay, my increasing stack address is this. Okay, this is 0000 FFFF, somewhere down here. Okay, so when you actually execute this instruction, move Z comma 0, we are assuming that the local variable Z is sitting in EBP minus 4. We will come to this. When you come to the translation of the function Fn, this will become very clear why it has to be EBP minus 4. So therefore, the local variable Z will basically come and sit in this particular memory location in the stack. This is the stack segment, what you see on the right. Then in C101, now here is another important thing. I have just assumed that next byte is the next instruction, okay? But typically this will be more than 1 byte, it will basically be 4 bytes, some 32 bits at least and so on. But notionally I am assuming that the next memory location is what I am calling as C101, okay? In reality you have to translate this to something else. It might actually be C104, right? If it has to be a 16-bit address along with a 4-byte offset for each instruction, okay? But notionally, let's just go with this. So now what do I do? Before I call the function Fn, I am going to push 4 onto stack. Now when you push something onto stack, remember my stack pointer decrements, okay, by 4. Okay, this is a constant and we have pushed a 32-bit number onto stack. Again I push 0x0 all 2, right? And again the stack pointer decrements by 4 once more, right? Now I am going to call the function which C200, and I am assuming that the function Fn will sit in this. Now this address typically is not known to the compiler. Okay, I am just talking of a compiled and linked code, with all the address translation done. This is how it will look. Otherwise, it will just assign some label for now. The compiler will take care of putting all this in memory and stuff and getting you the whole actual addresses. So let us assume that the function Fn is sitting in location C200, somewhere else in the code segment, right? Now when you execute call C200, right, the instruction pointer is already pointing to C104 because that's where the next instruction is sitting in the code segment, okay? And therefore when you do call, right, what will happen? First the return address, that is C104, will get pushed onto stack, as you can see on the right. So when you do call C200, first C104 will get pushed onto stack. That means ESP will now decrement by 4 again, okay? Now this is exactly what I told you, that something in the stack is implicitly happening when you call a function, right? So if you look at the stack segment on the right hand side, this C104 is sort of the return address, right? Now all of this is going to be local variable space of main, of the function main, right? Implicitly this return address C104 has demarcated something for you to say, okay, below that everything is local variable space of main, above that you are now going to enter a different function, and that is why the stack segment is ideally suited to implement the idea of scope of a local variable. Okay, therefore now what you do, you are now going to, having pushed the return address C104 onto the stack, you are now going to load the instruction pointer with C200. Okay, so the instruction pointer, by the way, this is the instruction pointer, whatever you see, right? I think that would have been implicit by now. The instruction pointer is now moving in the code segment. On the right, I am showing you the stack segment. Okay, these are the two segments of interest in order to understand the flow of a program. So now when I look at the assembly translation of the function fn, okay, what do I need to do? This is what we need to understand, okay, because remember when we did main, I just told you that z is stored in EBP minus 4. All that we will now understand how it is the case, okay. So this local variable z, right, I also told you is going to be in EBP minus 4. Currently my EBP is pointing to something in main. So remember, anything below is that of main, the calling function, right, local variable space of main, and therefore it is not something that is even meant for this function fn. So when you enter this function fn, remember the local variable z, which is also stored in EBP minus 4, has to now point to a different location on its own stack. Therefore, the first thing you need to do is to move this EBP out here so that you can get a new local variable space for access. Okay, so that's why the first thing you do is to move, you execute this instruction, which is move EBP comma ESP. So whatever is in ESP will get loaded into EBP. EBP has come here now. Okay. Now think about the following situation. Okay, I told you that as a programmer you don't worry about allocating space in memory for local variables, right? But the compiler has to do this for you. Someone has to say that this variable space is meant for this function fn, right? Otherwise how can you guarantee that nobody will override that? For example, if I do not allocate any local variable space here, okay, for the local variable of function fn, and let's say I call another function. So let's say I simply put the local variable z out here of fn. Okay, I allocate some space here and then I do a call. What will happen? The stack pointer is pointing here. The call will just override this. Why? Because that return address will get onto the top of the stack, right? And therefore I need to do some allocation of local variable space, and that is exactly what this sub ex0x40 is doing. So what are you doing? You are moving the stack pointer out so that you do any call, writ, push, pop, whatever you want you do, that will happen above this space. So you are allocating a block of memory in the stack which says this is local variable space meant for this function fn. Okay. Now who decides whether this subtraction should be 0x40 or 0x64 or 0x100? That is taken care of by the compiler. How does the compiler know? The compiler knows how many variables are exactly present, how many local variables are there, and how much memory you need on the stack. So if there is only one or two variables, it will guard band and just push it out by 64 bytes. 0x40 is 64, right? it will just give 64 bytes, right? And then you go ahead and do this move contents of EBP minus 4, right? Now I am telling you, understand, you can see why local variables have to be stored as EBP minus n. So all this local variable space, right, of the function fn, if EBP is now fixed to this location here, if EBP is here, this is EBP plus 4. This location here is what? EBP minus 4, right? So anything above on this picture here is local variable. Anything below has to be a function parameter, if a function parameter was passed to this function. Okay, that's why we made this statement earlier. So therefore, again let me take off all this. Okay, so what do I do now? I do move EBP minus 4 comma 0. So the local variable z is in the same EBP minus 4, right? Remember, this is EBP minus 4. The local variable z in main was also EBP minus 4, but EBP was pointing to a different location there at that point, right? Now what do? I want to do z equal to x plus y, and we just said move EAX comma x. What is x? It is EBP plus 4. What is y? It is contents of EBP plus 8. Sorry, x is contents of EBP plus 4, y is contents of EBP plus 8. Okay, so this is with respect to that function EBP plus 4, and this is EBP plus 8. And that's why you do move EAX comma E contents of EBP plus 4, right? Then you do add EAX comma EBP plus 8, right? Now you would have performed the addition, and EAX after this instruction would have what? 0x 0 0 0 0 6. Okay. Now what do? I am going to do move contents of EBP minus 4. What is contents of EBP minus 4? It's a local variable z of function fn. I am going to move the value of EAX, and therefore I have put 0x all 06, that answer, into the local variable space in the function fn appropriately. Okay. Now I did some subtraction of ESP, right? So remember, anything that you do to the ESP, you have to undo before you come out of the function. Otherwise, if you execute this instruction directly, what will happen? It will treat this top address, whatever this address, whatever the data here, as the return address that you have to go to, and it will load EIP with that in the next step. So therefore, you must be careful about this, and you cannot just blindly do a ret. You have to undo the subtraction operation on ESP by doing add ESP comma 0x40, bring ESP back to the top of stack where it was before it entered the function. That is where the return address C104 is. Now you do RET. When you do RET, it pops the top of stack, right? Remember, it has now popped the top of stack, so my ESP has incremented and come here, and then it will load the return address C104 to my thing. That's why the instruction pointer now is pointing to C104. Okay, that's what the ret instruction does. Now what do? I say move EBP minus 4. So the local variable z in main was also EBP minus 4, but that was sitting here, right, in this place. However, we have gone to that function, we have done something, and that EBP is now pointing to a different thing. So when you do move EBP minus 4 comma EAX, why EAX? Because the return value from the function fn is going to come through EAX. That is an agreed protocol, right? But now when you do this move EBP minus 4 comma EAX, you have accessed the local variable z of Fn rather than accessing the local variable z of main, and therefore it is a stack corruption. Okay, that z of Fn has gone out of scope and you are not supposed to actually access it, right? So this is where the problem is, right? Now fine, we basically load the return value EAX into some global variable, and let's say I do a return from here. I do a return. What will happen? The top of stack ESP is pointing to this particular data. When you do RET, top of stack is simply popped onto the instruction pointer. That's what RET does, right? Now that is now pointing to some arbitrary function parameter that we pushed onto stack. That's what the problem is, and this is what I told you. Every push or every stack operation that you do, you must undo before you exit that function. What is the function we are executing? Main. Okay, and therefore when you do this without undoing that push, you will land up with this problem. Your computer is simply going to reboot after this operation, right? So therefore, in summary, our first naive translation to assembly language has failed because of two reasons. One, right, the failure, right? What is the failure? One, EBP was pointing to function local variable space, right? To my function, parameter push was not undone. Right, this is the issue. Okay, therefore if we want to now translate this C program to assembly language, we need to fix these two problems.